This is Coulomb and Lorentz, the first video in the Introduction to Electricity and Magnetism series. Electric forces are extremely strong. Let's say I give you two protons. Since they both have mass, they'll feel some gravitational attraction. However, the electric repulsion they'll experience is 1,235 million billion 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 times stronger. In this video, I'll explain Coulomb's law and Lorentz's law, which govern how charged particles exert force on one another. Let's establish some notation first. I'll use the vector r for the displacement between 2 points, with the tail of the vector usually at the origin and the tip somewhere in space. The scalar r is the distance between those 2 points, that is, the length of the vector r, and r hat is the unit vector in the same direction as the vector r. We are now in position to explain Coulomb's law, which specifies the electric force caused by some source charge on another charge, called a test charge, at a distance of r from the source. Electric force equals the product of the source charge and the test charge, times a constant, divided by r squared, and points in the direction of r hat. That means the strength of the force is directly proportional to the amount of source charge. If I double the charge, I double the force. If I flip the sign of the test charge to negative, then I flip the direction of the force. So far, we've only discussed the force exerted by one point charge on another. To work in more general circumstances, we'll need to know how to put together the forces exerted by many different charges. In theory, this could get quite complicated, with the exact relative positions of the source charges adjusting the total force through second-order sensitive interactions. The principle of superposition says that, in fact, the forces come together in the simplest way possible. The total force is just the vector sum of the individual forces. Since integrals are the continuous version of sums, this also means we can compute the electric force exerted by some distribution of charge by integrating over space. To deal with more complicated charge distributions, we need to introduce electric fields. The idea is to take everything in Coulomb's law except the test charge and put them all into one term, E. E is a function from R3 to R3. So every point in space is assigned a vector. That vector tells you how much force would be exerted per unit of test charge at that location. Using the principle of superposition, the electric field of 2-point charges is just the vector sum of the fields induced by each of those charges individually. And that's actually how I made this background in MATLAB. The quiver plot at each point was just the sum of the field vector induced by the positive charge at 0, 1/2, 0, and the field vector induced by the negative charge at 0, -1/2, 0. When you're first learning about some new physics concept, it's helpful to figure out what its units are. A coulomb is the amount of charge in about 6 billion billion protons. For sense of scale, that's approximately 1/10,000,000th the number of protons in a liter of water. The electric constant Ke has units of newtons times meters squared per coulomb squared, since the inputs to Coulomb's law are charges and distances, while the output is a force. Finally, the units on electric fields are simply newtons per coulomb, since the electric field tells you how much electric force would be exerted per unit charge. As an example of the use of electric fields, and in order to use some multivariable calculus, I want to calculate the work done by an electric field. If you need a refresher on work and vector line integrals, you can look back at section 16.2 of Stewart. Professor Hall also made a nice video recap of the topic on chimera. Without further ado, let's start analyzing the terms in this integral. E is the field induced by the charge big Q at the origin. dr represents an infinitesimal displacement vector. Once we parameterize our particle's path from 2, 4, -4 to 1, 2, -2, we can differentiate to find that dr equals -1, -2, 2 dt. Now we can substitute in our expressions for E and dr and take that dot product. What's left is just cleaning up the terms and finally integrating, so I encourage you to pause the video here and try it for yourself. Since the parameter t runs from 0 to 1, the absolute value in the denominator there, once we clear away constants, is the quantity 2 minus t cubed. By setting s equals t minus 2, we can get the integrand into a form we know how to deal with. Minus 1 over s squared is the derivative of 1 over s. Evaluating, we find that the work done is equal to minus ke little q big Q over 6. As a sanity check, the answer should be negative, since electric force is pushing back against the direction of motion. Now let's move to the second half of this video and introduce magnetic forces. Unlike electricity, there are no magnetic point charges creating magnetic field. I'm going to put off until a later video the discussion of how magnetic fields arise and just explain how magnetic fields can exert forces. The first major difference between magnetic fields and electric fields is that magnetic forces act only on charges in motion. By convention, magnetic field gets the capital letter B. Lorentz's law states that magnetic force equals the test charge times the cross product of the charge's velocity with the magnetic field. So the second major difference between magnetic and electric fields is that magnetic forces are always perpendicular to both the direction of motion and the magnetic field itself. Let's have a look at the motion of a charged particle under the influence of a uniform magnetic field. If a negative charge is moving with constant velocity in the positive y direction and encounters a magnetic field in the negative z direction, the particle will sweep out a semicircle in the positive x direction in the region of the magnetic field. Here, the magnetic force acts as a centripetal force, keeping the particle rotating like a planet around a sun. The centripetal force for an object in orbit is mv squared over r, mass times speed squared over radius. Therefore, we can compute the particle's original momentum, knowing only that it rotated with radius r in magnetic field B. That way, if I fire lots of unknown particles into a uniform magnetic field, I can figure out whether their charges are positive or negative, and their momentums, by tracking where they exit the magnetic field. So, what are the units on magnetic field? By analyzing Lorentz's law and filling in the units where we can conclude that the units of magnetic field B are Newton seconds per Coulomb meter. I'd like to leave you with one last example, this time of magnetic and electric forces acting at the same time. Suppose E is pointing everywhere in the positive z direction, while B points in the positive y direction. What trajectory will a positively charged particle follow?
Yeah.